Welcome to the first experiment in C343. This experiment is going to be on the effect of pH on a food preservative. So everything that we're doing in this lab and in organic chemistry in general is solving chemical problems. Even though the things we do are kind of elementary, there are some really big, commercially important and societally important problems that chemists tackle all the time. Some of those questions are on the screen. You can see using and storing solar energy, decreasing waste and hazardous materials, finding alternative fuel sources, curing diseases, creating semiconductors, superconductors. Those kind of things are extremely important in the world as we go ahead, and eventually those are going to be questions that organic chemistry can answer. To solve scientific problems, you guys I'm sure have seen at this point the scientific method. So this is something you might have even learned as early as high school. Defining a problem, getting a plan, getting some evidence together, getting some kind of hypothesis, testing that in the lab, and then getting some conclusions based off that. So we'll be doing that kind of thing in the lab, but with some slightly different twists. A lot of times the problem is going to be given to us in the lab book as well as the plan. So that's usually in some of the pre-lab reading you'll get. The evidence, again, is usually found in your lab book. Sometimes we might ask you to go out and look for external sources, especially on some of the end of the semester projects. Then once you evaluate what the book says, that evidence, then you look at the hypothesis that they provide. You get to test it by doing the procedure they give you in the book, and then you can evaluate that data and see if that hypothesis that either they or you developed was correct. So in order to do all these, you've got to have some fundamental theories and concepts to apply this past knowledge to new problems. So as we go through, you're not just going to be working on procedures, you're also going to be seeing theory thrown in so that you can answer these problems by making informed decisions instead of just following what the book says. So looking at solving problems just in the case of an introductory organic lab sometimes can lose some of the luster of problem solving. A lot of times these things were crucial to survival and huge societal importance. A major example that I just kind of pulled off some research was chemical warfare. So phosgene, mustard gas, sarin, VX, you might have heard of some of those chemical warfare agents. Those were developed in World War I and II. And were used sparingly in some of those wars. Sarin and VX specifically, you can see sarin over there at the right, are organic molecules that are part of a class called organophosphates. So those things are really extremely potent, irreversible cholinesterase inhibitors. So when those things are introduced to the body, instead of acetylcholine, once a nerve impulse fires, acetylcholine is that trigger agent, and then acetylcholine is allowed to break down. So with these inhibitors, acetylcholine can't break down and the nerves just keep firing. So eventually that leads to muscular tremors and death. You may have even seen that happen in The Rock when Nicolas Cage was exposed to the VX gas. So a solution to this was atropine, which is again another organic chemical, is something that binds to some of those receptors that sarin and VX gas might interfere with, and that chemical atropine doesn't cause these continuous muscle contractions. So organic chemists had to set out to synthesize enough atropine that these could be readily supplied to all the field medics who would be out on scene in World War I or II, so that if chemical warfare agents were employed, then they could immediately deliver atropine to a major artery. So you can see the top synthesis involved more than 10 steps. That synthesis was developed in 1901 and gave from the start to the end about a 0.75% yield. So that's less than 1% yield. That's a lot of wasted material. And if you start out with, a kilogram of starting material, you're not going to end up with too much, which is going to leave people in the field short of this antidote to the chemical warfare agent. So in 1917, the synthesis on the bottom was designed that uses really simple chemical building blocks, and eventually led to greater than 90% yields for the exact same thing. So a major development that helped get atropine to people who needed it in World War I or II. And as an example of how things can play off each other, this synthesis of troponone, which is actually a precursor to atropine, eventually helped solve the structure of cocaine. So sometimes solving problems can end up leading to solving other problems. So now we really get down to kind of sorting out and organizing organic chemistry lab work for you. Since you're just starting this, you probably haven't been through too many labs, Gen Chem and some stuff in high school. But organic lab work can be easily broken down into 5 categories. So everything that you're going to do in the lab is one of these 5 things. So either researching the organic reaction, so taking organic chemicals, adding them together, sometimes heating them, sometimes cooling them, so that some reaction takes place. Once that's taken place, then you try to separate, kind of an initial separation of byproducts or starting materials away from your product. And then purification involves further purifying that desired product that you're trying to attain. And then finally, you've got to analyze that product to identify that it's indeed what you want, and then also that it's pure. And that's using a set of specialized tools and instruments that we'll get into later in the class. So in order to go through those 5 steps, you guys are going to need some common lab tools. Some of the major glassware tools, a lot of these are probably familiar, are listed on the screen. So you've got anything that can hold an organic reaction, anything that can lead to separating things, maybe separating a solid from a liquid like some kind of filter. You've got things that are used for purification, and then we'll eventually see some tools that are used for analysis. So obviously there's some more sophisticated tools than just glassware. These are some of the larger instruments that we'll be using this semester. Melting point apparatus obviously takes advantage of using the melting point characteristics of compounds to identify them. And then there will be some others, NMR spectrometers, FTIR spectrometers, and gas chromatography, mass spectrometry, that we're going to be using throughout the first and second semesters. So now that we've gotten the introduction out of the way, let's actually look at what experiment 1 is asking. So they give you a little bit of background on what's going on, but they basically lay out the problem, wanting to know what happens if you ingest sodium benzoate. So is there a new substance formed when you take in this food preservative? You can see the structure down there in the box. So if you eat something containing sodium benzoate, it's ingested into the stomach, it may or may not chemically react there, and then may or may not create something harmful. So what we do find, and what your book tells you, is that sodium benzoate is often packaged with acidic foods, and most likely 99.9% every single one of you guys have ingested sodium benzoate at some point or another. And I brought out the blue drink from Prairie Farms. That thing contains sodium benzoate, as you can see underlined in the ingredients there. So knowingly or unknowingly, you've probably ingested it. What happens when this water-soluble organic salt, sodium benzoate, is ingested? So in order to get any kind of actual answer to this question, we've got to think about what happens when you ingest sodium benzoate. It goes into the stomach, which you guys probably all know contains HCl. So there's a complex system of hydrogen pumps that maintains a certain acidity in your stomach. So the normal stomach is below a pH 2, containing mostly hydrochloric acid. So if we were to simulate sodium benzoate in your stomach, we're going to use hydrochloric acid in place of that. So what we see, and you can see in this reaction on the screen, sodium benzoate when mixed with HCl below pH 2 is going to lead to a conjugate acid and conjugate base. Now that organic salt, the water-soluble salt on the left, turns into a completely organic molecule called benzoic acid. So now this becomes a chemical reaction. Even though it's simple acid-base, it's a chemical reaction that's occurred. You'll also notice that there's some curved arrows. If you're in lecture right now, you're probably learning about mechanisms. If you haven't already, you may be soon. So what those arrows mean is that a lone pair on oxygen is going over to form a covalent bond with hydrogen. Then the electrons between hydrogen and chlorine get put onto chlorine as a lone pair. So now you form sodium chloride and the oxygen picks up that hydrogen. So a major question is, does this equilibrium lie to the right or left? So is this reaction going to end up in mostly the product on the right or mostly the sodium benzoate that's left over there on the left? So to answer that question, just like you would have done in equilibria in Gen Chem, we've got to see which of the two sides contains the stronger acid. So on your screen is something called a pKa table. This is extremely essential to understanding some of the major concepts of the organic lecture too. So some things we do in lab aren't crucial to the lecture. This is 100% crucial. So make sure you get this point. Don't just skip over it. So looking at our two materials that we had a carboxylic acid. So that was the product in the reaction on the last slide. So a carboxylic acid uses the notation R and then a carbon double bonded to an oxygen with an OH attached. So that's kind of the generic form for benzoic acid, which is there on the right in the box. So if we look down, we can see that that generic abbreviation RCOOH is that blue box that's kind of lower on your screen. So if you scan over to the right in that box, it says the pKa is 5. So that means on a scale of, you can see -10 here to almost 50, the carboxylic acid functional group has a pKa of around 5. HCl, which you guys are much more familiar with, has a pKa of -7. So those two things are 12 pKa units apart, and since the pKa is a log scale, it's even greater than just 12 units. A good rule of thumb to follow is that if two different acids are more than 3 pKa units apart, then the lower pKa number is a significantly stronger acid. So if it's a stronger acid, like in this case HCl is, then that's going to affect how the equilibrium works, and it's going to end up going away from that strong acid, which is going to lead to more of the benzoic acid product. And remember from Gen Chem, the reason why you have these lower pKa's is that when you remove the hydrogen, those conjugate bases are very stable. So if you look at the bottom right corner, you have methane, CH4. If you take one of those hydrogens off, you have a negative charge sitting on a carbon, which is not necessarily a stable organic molecule. So that has a really, really high pKa because it doesn't want to lose that hydrogen. The conjugate base is not stable. Whereas something like HCl has a really stable Cl-. It's got the noble gas configuration, and so losing H from HCl is a pretty manageable thing. So the pKa table is going to be really important in organic chemistry to see how acidic different hydrogens are on organic molecules. It won't just be hydrogens on inorganic acids like hydrochloric or hydrobromic or sulfuric acids, but any single hydrogen on an organic molecule can be considered as an acid, just maybe not that good of one. So organic chemistry does not nearly use as much mathematical equations as Gen Chem or you might have in high school, but I do want to remind you of a couple equations that you guys should be familiar with. pH, which is there on the left, and then the Ka equation, which is there on the right. So if we want to solve this equation to try to understand how far that equilibrium lies to the right, because remember HCl was much more acidic than the benzoic acid. So the stronger acid, HCl, the equilibrium will always lie away from that. So the equilibrium should lie strongly to the right to form benzoic acid. But we can prove that using those two equations that we have for pH and Ka by using some algebra, knowing what the pH is, assuming that the pH is 2, and then using the pKa for benzoic acid. On the last slide we saw carboxylic acids were around 5 for a pKa. So in this case benzoic acid is 4.2, which is pretty close to 5. So if we plug in those values for the numbers you see below, we end up with a ratio of C6H5COOH, so that's the product, benzoic acid, and then on the bottom is sodium benzoate. So our ratio is 155 to 1. So for every 155 molecules of product, there's going to be 1 molecule of sodium benzoate starting material left over. So at a pH of 2, we can see that the equilibrium definitely lies very far to the right. So since we just calculated that at pH 2 or below, we're going to have almost exclusively the product, so the equilibrium lies to the right. So from that, you guys are going to need to do a pre-lab calculation in your notebook that finds the theoretical yield of benzoic acid. So you're going to start with 2 grams of sodium benzoate, and then assuming that it goes completely to the product, what the theoretical yield is. So remember, use molecular weights to get to moles and find that theoretical yield. All this should go in your pre-lab calculation section of your notebook. Alright, so now that we've gone through and convinced ourselves we know that sodium benzoate forms benzoic acid in the stomach, we've got to see, since we're simulating this, what the characteristics of sodium benzoate, the starting material, and benzoic acid, the product, what characteristics could we use that show those two things are different. One thing you'll notice, and we talked about, is that sodium benzoate is a salt. So it's got a negative charge, a positive charge, and it's what's called an organic salt. Sodium benzoate has to be water soluble because in order to preserve that blue drink that we saw earlier, unless it's water soluble, it's going to sit at the bottom of that container. So we know sodium benzoate is going to be soluble, but the benzoic acid is no longer a salt. It's a completely organic molecule, and we know that things that are organic, that have carbons, are not nearly as soluble in water. So are those two different compounds? Yes. Benzoic acid is not a salt, and it's an organic molecule about 200 times less soluble in water than sodium benzoate. It also asked in the hypothesis if this new compound, benzoic acid, is harmful, but the book even answers that. It tells us that benzoic acid is found in natural sources like cranberries and prunes and cloves, so it's no more harmful than sodium benzoate is to begin with. So when looking at these two things, the most likely of those three observations at the bottom that's going to occur is precipitation. So we've got something very soluble in water, sodium benzoate, and something that's not nearly as soluble in water, benzoic acid. So this reaction is very nice that we can visually see the reaction occurring by precipitation. So So the tools that you're going to need in the lab, the main glassware apparatus for this experiment is called vacuum filtration. And if you go onto YouTube in the IUPUI Organic Chem channel, you'll see a video demonstrating how to use the vacuum filtration apparatus. So in that video it shows you all the different parts. You can see them labeled here. I'm not going to go into it in too much depth because that video does a good job. But remembering, benzoic acid is not soluble, or is very poorly soluble in water. When we're filtering away our precipitated product from the rest of the liquid in our reaction, this vacuum filtration is going to allow us to collect that benzoic acid while the rest of the contents of the water-soluble portion of the reaction filters straight through. So make sure that when you're filtering this, use all those ideas that the video talks about, and make sure that you use just a little bit of ice-cold water if you're trying to rinse out your reaction container, or if you're trying to just rinse off the filter. Because if you use lukewarm or even warm water, benzoic acid is going to start being little by little more soluble, and you might end up getting a lower yield of benzoic acid on your filter paper. So once you get that filter paper, you're going to let it kind of dry on the vacuum filtration apparatus, and then eventually, once that product dries overnight or over several days or a weekend, you're going to be able to scrape that solid off of the filter paper, being careful not to scrape too hard to get any of the filter paper itself, and you'll be able to scrape that and get a actual yield when you get a mass on the balance. So that part of the experiment takes care of most of what you'll be doing in the first lab period. The first experiment, just because it's introductory, actually has a little tag on, so it's called Part B in your procedure, and it's asking you to find the density of an unknown solution. So really it's a good introduction to using the pipetteman. So you can see a drawing at the bottom left there of what a pipetteman looks like. Your TA will give you a little bit of a demonstration in lab. That pipetteman should be preset to a certain volume. So those are used to transfer small volumes in pretty decent accuracy. So what you're going to do is take a pipetteman that should be preset, and you're going to consecutively add a mass of some unknown organic solution to a tared beaker or vial on the balance. So when you've got that thing on the balance, the beaker or the vial, and you add a certain preset amount of liquid, which is one of those 5 liquids on the right, then a certain mass is going to result. So you put in a preset volume, a certain mass is going to result. You add a little bit more volume, a second injection, and then you end up getting more mass. So you're going to graph these volume additions by the pipetteman on the x-axis, and then the resulting masses that you get from the balance are going to become the y-axis. So once you've gotten that x and y laid out, you can plot your points, and then the slope of that line is going to be the density. So you're going to have to go on to Wikipedia or into some kind of chemistry reference book to find the densities of those 5 unknowns, and then match up your unknown to one of those 5. So the density you calculate should be relatively close to one of those, and hopefully right on. So once you do that, make sure in your lab notebook that you include that graph and the results of Part B, even though it's just kind of a tag on to Experiment 1. So I hope your first narrated PowerPoint went well. Definitely feel free to ask your TA questions, email me questions. A lot of this information is going to end up on the quiz, so hopefully it's clear and you understand it. If not, make sure you let one of us know, and we'd be happy to help you. We'll see you in the lab.